Hi everyone. So we're going to be working on the Taylor series. So we're going to be working on Taylor series day 2, or it's day 4. I can't keep track of it. Actually, weirdly enough, it's actually going to be day 5. We're just going to keep changing the dates. It's fine. So today what we're going to be working with is we're going to be talking about how to actually implement some of the Taylor series to kind of help us along with certain things. So the first one I'm going to start off with is sine of x is going to be equal to we're going to start off with that being x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on and so forth. Now, the idea here is that you want to try to, this is what they actually had to do back in the day when we didn't have calculators and other things to actually calculate the values. So we're going to start off by trying to figure out, or in a sense, estimate the value of, like, let's say, sine of 1. Now to estimate the value of sine of 1, and then let's say that we want the error to be less than 1 over 1,000. So from the alternating series bound that we talked about before, we can actually use some of the things that we're familiar with to be able to figure those things out. And I'm actually going to do this without a calculator, and they might actually ask you to do the same. So I'm going to say sine of 1 is going to be roughly equal to, now anywhere there's an x, specifically in this series, I'm just going to place in a 1. So it's going to be 1 over 1, or excuse me, 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. And if I actually write down some of those values, that's going to just be 1 minus 1 over 6 plus 1 over 120, and then minus 1 over 5,040. Now, you should still be able to figure out that specific number, the 5040, without a calculator. But nicely enough, that specific number is going to be, in a sense, smaller than 1 over 1000. So the error is actually going to end up being, in a sense, if we focus on those first 3 terms, the error itself is actually going to be less than 1 over 1000. So if I just do, let's say, this specific sum, so we're going to say 1 minus 1 over 6 plus 1 over 120. That's going to be equal to 0.84166. Now, you wouldn't be able to do this without a calculator. I'd probably say that they wouldn't, actually really ask for the number. But what they might ask is for just you find a common denominator. So in that case, that's going to be 101 over 120. Now, what we would say here is that the error, specifically, for that specific digit, right, this specific number, is going to be, well, whatever the absolute value of that error is going to be less than the absolute value of negative 1 over 5040, which is also going to be less than 1 over 1000. So which means that the specific value that you get for this is going to be, it's going to have more accuracy than 1 over 1000. And if I were to actually do sine of, let's say, 1 in my calculator, I'm going to get 0.84147, and then I can kind of compare it to what the actual value would be. And so in this case, I'm going to take, in a sense, what the actual error is. I'm going to figure out the error by figuring out the specific sum minus, in a sense, this is a partial sum of 3 terms. And I'm going to compare it to whatever that value is supposed to be. So this is going to be 0.84147 minus the other one, which is going to be 0.84166, and I should end up getting 0.000195, and so on and so forth. So this right here specifically is my error, and that number itself is definitely going to be less than 1 over 1000. Okay, seems pretty good. This section right here, when we're dealing with a lot of decimals, that's going to be most likely going to be a problem that is going to be within a calculator. So if they were asking you, let's say without a calculator, you'd be able to get 1 over 120, but you wouldn't actually be able to kind of prove it in terms of mathematically, the error and stuff. So then it says find the series in the form of, so like let's say that I was trying to figure out the integral of 1 over, or excuse me, the integral from 0 to 1 of sine of x squared. How could I figure out that value? Because if I try to do some type of integration with this, integration by parts, partial derivatives, or partial integration. It's not going to work out. So what I can do is I can actually make this series, so sine of, let's say, x squared, and then yet again, anywhere there's an x, I'm going to rewrite it as an x squared. So this is going to be x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, and so on and so forth. Now, why the exponents are kind of increasing this way, remember we want to, when I do a power of a power, the exponent specifically is being multiplied. So that should give you the value. Now, if I were to say, what is the integral from 0 to 1 of sine of, let's say, x squared? That is, in a sense, well, the integral of each one of those values. So what is the integral of x squared? Well, that's going to be x to the 3rd over, well, 3 minus x to the 7th over 7 factorial, or excuse me, 7 times 3 factorial, plus x to the 11th over 11 times 5 factorial, minus x to the 15th over 15 times 7 factorial plus dot 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 dot, and then we're going from 0 to 1. Now, the nice thing here is that since it's 0, the lower bound itself is just going to be all 0 itself. So the only real value that I'm trying to figure out is, well, when x is equal to 1. So it's going to be 1 over 3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus 1 over 15 times 7 factorial plus dot 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 dot. Now let's say that I wanted to try to approximate the error to be, yet again, same thing as before. I want the error to be less than 1 over 1,000. So I actually end up doing some of the calculations. I use some of just some of the multiplication that's kind of tied in with this. So it's going to be 1/3 minus 1 over 42. And then this is going to be plus 1 over 1,320 minus dot 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 dot. And we can see that this specific number right here is under 1 over 1,000. So we can say that this is going to be our error. And this is actually going to be my accurate number, which in this case is going to be 13 over 42, which is going to end up roughly being 0.3095, so on and so forth. Okay, so then I can say that the error itself is going to be 1 over 1,320, which is going to be less than 1 over 1,000. Right, and then remember that's also the absolute value. So we can say that this specifically right here is going to yield my error. And then if I did want to compare the integral from 0 to 1 of sine of, let's say, x squared dx, if you type that in your calculator, you should get 0.310263, so on and so forth. And then if I wanted to actually try to figure out the actual error, this is going to be the absolute value of 0.310263, what I just wrote down, minus this value right here, 0.30995, so on and so forth. That's going to yield me a number 0.000744, and then that goes on forever. So pretty accurate to, in a sense, 3 decimal places, which is pretty solid. Okay, let's move on to the next one. So if I were to say, I want you to write the first non-zeros for, like, let's say e to the x, that's going to be 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial plus dot 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 dot. Remember, you need to make sure that you have that specific thing memorized. Also, the general form, so x to the n over n factorial is my general. And then remember, it keeps on going forever. So if I were to say to you, let's say that f of x is going to be equal to e to the x. And I want you to find the limit as x goes to 0 for f of x minus 1 over 2x. Now, if I were to do this the old-fashioned way before we start even talking about series, I can say e to the x minus 1 over 2x is going to be equal to, well, if I do a direct substitution, that's going to give me 1 minus 1 over 0, which is just going to give me 0 over 0. And then, right, I can use L'Hopital's to figure this out. But I'm not going to end up doing this. I'm going to make this much more complicated because, you know, math is fun. So I'm going to rewrite f of x as the Taylor series right here. So I'm going to rewrite this as the limit as x goes to 0 of 1 plus x squared over 2 plus x to the third over 3 factorial plus x to the fourth over 4 factorial, so on and so forth, dot, 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 dot. Close parentheses, right, because this is, in a sense, e to the x. Then it says minus 1 over 2x. Okay, so if we think about how this goes, each of these specific terms right here all have an x to them. So they're not constant. But the negative 1 and the 1 right here are the only constants in a sense, this numerator. So those are actually going to cancel. Now I can see I can see here that I have a 2 on the bottom, and I also have an x on the bottom. So each of these exponents right here are all going to reduce, and I'm also going to have another 2 added on the bottom. So the first one is going to just be, in a sense, what am I missing? I'm missing a term. Oh, I'm missing x, which is actually kind of by far the most important one. So I'm going to have 1 plus x. So yet again, same deal, right? The 1's cancel. So if I do x divided by x, right, that gives me 1 over 2 plus x over 2 times 2 plus x to the second over 2 times 3 factorial plus x to the third over 2 times 4 factorial, and so on and so forth. Now we can see here that each one of these terms right here are all going to have an x, while this 1/2 is my constant out in front. So if I'm trying to figure out the limit as x goes to 0, all of these values right here are all going to be 0. So 0 plus 1/2 is going to end up giving us 1/2. All right, and the last problem that I'm going to be working with. Let's say that I want the first 4 non-zero terms of e to the x cosine of x. Okay, so this is where things get really, really interesting, also kind of a little bit of a pain in the neck. So I'm going to write down all the series. So I'm going to write down e to the x is going to be 1 plus x's second over 2 factorial, plus x to the third over 3 factorial, plus x to the fourth over 4 factorial, and so on and so forth. Cosine, on the other hand, that's a terrible cosine. Cosine is going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Now, the interesting part here is that we can see a couple things that are in relationship to these values. So we can see that, in a sense, they both have, like, let's say an x to the fourth. They both have an x squared that end up having the same common denominator. So it's almost kind of like this. Ready? So we're really doing 1 plus x to the second over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus dot 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 dot, close parentheses, and then times 1 minus x to the second over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on and so forth. And what I have to do here is kind of a little bit of a mess. What I'm going to be doing here is I'm going to be foiling, but not like any foiling that you've seen before, because I'm going to do, well, 1 times that, 1 times that, 1 times that, 1 times that, and then move on. Well, x times that, x times that, x times that, and x times that. And this is going to get kind of a little overwhelming in terms of how many exponents, and especially if I only want the first 4 non-zeros. I don't want to do too much, and I also want to think about, in a sense, the degree that I'm actually going to end up getting into. So what I'm going to do here is I'm going to actually start off by actually multiplying it like this. I'm going to do, well, 1 times 1, 1 times x, 1 times x to the second, 1 times x to the third, and 1 times x to the fourth. So I actually just end up getting, in a sense, the same series as e to the x. So 1 plus x squared plus x to the third over 3 factorial plus x to the fourth over 4 factorial. So I have an idea of, in a sense, how many terms there are going to be. Now, these are the first 4 non-zero terms, so it looks like it's going to go into, let's say, degree third, or the third degree. But you might not necessarily know if something is actually going to cancel. And in this case, there is actually something that cancels, so that's going to be a little bit of a pain in the neck. But, so this goes on forever. Then I'm going to do the next set. So I'm going to do 1 times, or 1 times negative x. I'm actually going to do this. I'm going to do negative x squared over 2 factorial. Well, I'm actually just going to say 2. And then that's going to be 1 plus x to the second over 2 plus x to the third over 6. And then plus x to the fourth over 24, and then plus ... So we can kind of continue this. By the way, when I multiply these in, I'm going to be adding them to these specific values afterwards. So I'm going to get negative x to the second over 2 plus, actually these are all going to be minus, so minus x to the third over 2 minus x to the fourth over 4 minus x to the fifth over 12, and then minus x to the sixth over 48. And that's going to continue going on forever too. Okay, then I'm going to, just so that we can kind of get too many terms that we don't necessarily need, I want to do x to the fourth over 24. That's going to be, and so it's going to be 1 plus x to the second over 2 factorial, which is just going to be 2. X to the third over 6 plus x to the fourth over 24 plus ... Okay, so this times that times that times that times that. I probably don't even need to go that high because it looks like that x to the fourth is going to be my last degree anyway. So x to the fourth over 24 plus x to the fifth over 24 plus x to the sixth over 48 plus ... I'm not going to continue with that. Okay, so let's focus on the terms. So it looks like that 1 is going to be the lowest. So I'm going to shrink this down. So 1 is going to be the lowest. Then I'm going to work with the x's. So it looks like I have an x there. That looks like the only x, so plus x. By the way, I'm not focusing on this, and I'm not focusing on this. I'm only focusing on this right here, and this right here. And I'm putting those things together. So it looks like, oh, I also forgot it over 2 right here. So it looks like that I have an x squared over 2. I have a negative x squared over 2. No x squareds on the bottom, but those two actually cancel, so that term actually goes away. So that's what I was kind of referring to. So that looks like x to the third over, in a sense, 6. I'm actually going to write that as 6. And then I have negative x to the third over 2. There's no x to the third for the last one, so just kind of off to the side, x to the third over 6 minus x to the third over 2. Find a common denominator, multiply by 3, so I get negative 2x to the third over 6, which is going to just give me minus x to the third over 3. Okay, so that term's dealt with, so x to the third, x to the third. And then it looks like that this is going to be my last term right here. So x to the fourth, x to the fourth, and then the last one, x to the fourth. So doing some simplifying, so x to the fourth over 4 factorial, which is going to get just be 24, minus x to the fourth over 4, plus x to the fourth over 24. So we're really saying 2x to the fourth over 24 minus x to the fourth over 4. Common denominator is going to be 24, so we're going to multiply by 6. We're going to end up getting negative 4x to the fourth over 24. The 4's cancel, so I'm left with negative x to the fourth over 6. So negative x to the fourth over 6 is going to be my final answer for, if I were to, in a sense, say the first 4 non-zero terms for e to the x cosine of x. So kind of involved for something so simple. It does require a lot of work, in a sense, trying to think about foiling and then how the terms and the values end up kind of going together. All right, that is it. I am finished for, in a sense, day 5 when dealing with Taylor series. I'll get back to you guys tomorrow for the next day. Thanks.